All right, boys and girls, welcome back to the drive-through. We're making our way to the end of the existence of calculus. 14.4, it will just cease to exist. All right, so hey, I want to start this by reviewing 14.1 through 14.3, just the concepts. What did we learn in 14.1? You learned about force fields, which are also called vector fields. Okay? You remember that? All right, now, within those, you learned about what it meant for a field to be conservative. Okay? And then you also learned how to show that a field is conservative. What did we learn in 14.2? That was line integrals. Okay, now line integrals, you did some things that you didn't like at all. Like you found the, air quotes, mass of a wire, and you didn't like that. Okay? On the quiz, there was a bonus question where you found the lateral area of a surface. That was a little more useful. Okay? And then you also did a lot of questions involving work, and you liked that because you could conceive moving through a force field and doing work because it's force times distance. Okay? You remember all that stuff? All right. 14.3, what was that? Conservative vector field. So it was like a more specific application of 14.1, right? And there's two really important facts from conservative vector fields. What were they? Excellent. Okay, I'm going to say that one second. Let's come back to that one because it's based on the first one. Yes, if the field is conservative, then the path that you take does not affect the work. It's independent of the path. That's a really important fact to remember about conservative vector fields. And since that's true, if the loop is closed, the work is 0. And the way to think about that is because you could choose to go the path that you didn't go anywhere, and then your distance would be 0 and the work would be 0. Okay? All right. So that brings us to 14.4. But before we get into Green's theorem, and just so you know, because I read the book, Green was the son of a miller, and he was born in 1800-ish. And he wrote this theorem in anyone got it? 1828, okay? It kind of helps to think about when these things were created because they were then applied to something. But before we get into Green, I want you to remember this. That's what you've been doing, okay? That's the same thing. Same thing as that. I need my DT because that's kind of the key to this, what we're doing right here. That's the same as that. And that is the same thing. Follow through on this because this is going to be the key to understanding what the heck you're doing. It's all the same thing, okay? It's all the same thing. Now, we are yet to use this at all. All we've done is, we've found a function of r for x and y that were our parameters. Does that make sense? I don't know if I'm saying that right. And we had a force field given to us, and then we substituted in our x's and y's. So everything was in terms of what here? Everything was in terms of t, and then we got our line integral on. You guys okay with where we're at right now? All right, well, here's Green's theorem. Okay? Green's theorem says if you have a line integral, So this is why we did all this. Whoops, plus n. That's just a line integral. Okay? But now you've got I probably should say traveling with a positive orientation. Okay? So what does that mean? Okay? That's what that means. The region or the area, if you're looking out your window, it's always on the left, NASCAR style. Okay? You're driving around your path, the region is always on your left. That's how you know you're going positive. Okay? Counterclockwise, exactly. Okay? If you've got that, if you've got a line integral over some force field with a positive closed loop, Green's theorem says that you can just, and we're going to talk about what it means, but I'll just write it like this. dn dx minus dm dy. Okay, so here's what he's doing. Instead of the complicated parametrization, write everything in terms of t and do a single integral. He's saying you can do a double integral and substitute that in, and we'll talk about what that actually means when we do an example. And that's the exact same result. So the question is why? The answer is because it's easier sometimes. Sometimes it's a pain to find the parametric, and it's a pain to substitute. Now, why does it work? I want you to think of this. Hopefully you followed that fundamental theorem of calculus discussion that we had. We're adding an integral, okay, and then kind of popping things in and subtracting the difference, which is the same thing we did for the fundamental theorem of calculus. Do you follow that? I'm not going to go back and redo that, but if you didn't, you might want to just rewatch that portion of the last video. That's why this works. Now, I'm not going to do any proofs on this video, so if you really, really want to learn the proof, which would be awesome, just read the section on page 1042. There is a proof there. Okay? So now let's see this in an example. So let's say you've got this. Y cubed dx plus x cubed plus 3xy squared dy. Okay, now are there any questions? Because there might be a good question for you to ask right now. Excellent, that's a good question. The question is, what are we actually finding? I'm glad you asked it, because that might lead to the question I thought you would ask. Okay, we're finding the work done through this force field, m comma n, over this path. The weird thing, it doesn't look like a path because we're writing in differential form. There's no r of t listed there. Excellent. That's the question I thought you'd ask. Why is it not 0? Because we're no longer dealing with conservative fields. Now, you might ask, how do you know it's not conservative? And shouldn't we do the test before we get started? Well, I don't think so, because if it's conservative, how are these two things related? And what's it going to give us for the work? Yep, they are. And what's it going to give us for the work? It's going to give us 0, because It's a closed path in a conservative field. So you can still use Green's theorem in a conservative field. You're just wasting some time. Okay?
Maybe this was answered in the last section, but why does a line integral give you the work?
It's force dot distance. So the line integral is calculating distance. And the force, when you dot it, we're just adding up a lot of little pieces of force times distance. Okay? The crazy thing is, how do we go from a one-dimensional work to a two-dimensional area and have it be the same thing? But that is what I'm finding out is why you really have to understand the fundamental theorem of calculus. Because I feel like here's what we're doing this whole section. All we're doing is we're doing calculus so we don't have to do hard calculus. That's literally what we're about ready to do here. Okay? So evaluate this over the path okay? Got it? So, to keep in mind, we've already done this question. We did it a couple videos ago. Could we find this in terms of t? We could find the parametric of this, pop all those t's in for these, and do it the way we used to. We're going to do it a different way, though, okay? So we are going to change this into a dA. I think I might need more room than that, so I'll wait for that. Now, do we want to call that thing vertically simple or horizontally simple? We don't like those words, but I can tell you I want x equals to be on the outside. So what's x going from?
0.
X is going from 0 to 1. What's y going from? From x cubed to x. Do you remember how to do these double integrals? Okay? Now, here's where we got to use Green's theorem. So in there, this is m, this is n, so you do dn dx first. You're going to have to put that on your note card. It's easy to mess that up. Okay? So what is dn dx? Right? Am I doing this right? Yep. Okay. Minus what? Well, dm dy minus 3y squared. And then I got to get this right. dy dx. Okay? That's going to be very important because I got to integrate with respect to the right thing first. So you get this. And we're actually just integrating 3x squared, right? dy dx. So that's the integral from 0 to 1 of 3x squared y as y goes from x cubed to x. So that's, and then I need a dx there. So that's the integral from 0 to 1 of 3x cubed minus 3x to the 5th dx. Right? Are you still with me? Okay, so we'll just go from there, and I'll tell you that maybe you recognize this answer, but it's a fourth. We've done that question already a different way. So we are taking a one-dimensional path which we can find the work done, and we are doing it by finding it using the area and a double integral. Okay? And we're doing that to make it easier on ourselves. You okay with that? Let's do another example. Okay? In this example, we'll find out that we can use any area system we want, including polars. So, we have this force field. It's the same one. Keep in mind it's not conservative. How do I know it's not conservative? Because we just found an answer for the last question. Okay, and we want it to travel around a unit circle one time. Sorry, not a unit circle. A centered circle whose radius is 3. Okay? So, what you do is you treat this as m and you treat this as n. So let's just start it by making it look like a line integral. We want the line integral of y cubed dx plus x cubed plus 3xy squared, excuse me, dy, okay? So that is in differential form. Now, we want to turn that into a dA. Any suggestions? Polars, right? Good. Okay? So, what's one thing that we often do when we use polars? What do we forget? So we're going to have to multiply by r. But if we go dr d theta, what's our inside limits? R goes from 0 to 3, and theta goes from 0 to 2 pi. Okay? Now, let's leave it in terms of x's, and then we'll substitute on the next one, because it's going to be a little simpler. So, take the derivative of this with respect to x. What do you get? We just did this, but you know, if we didn't had just done this, and then minus, and then we're going to switch that eventually to r dr d theta. So now we get 0 to 2 pi, 0 to 3 of 3x squared. Well, what's x? X equals r cosine theta. Okay, like that. Now I need my r dr d theta. You could integrate this by using some u substitution, but just pop it in your calculator, and you end up getting 243 pi over 4. And that would be, that would be your work. Okay? Alright, just one more thing for the video. This is how math works. So, always, you know, it seems like you're working really hard to figure out one way to do it, and then you kind of use that and flip it against itself. Well, that's what we're about ready to do now. So, somebody, namely this green guy, was like, hey, it might be a lot easier to do our line integral by finding the area. Well, then that means that maybe sometimes it will be easier to find the area by doing what? The line integral, okay? It's just a flipped way to think about it. So, there's a proof for this, but let me just tell you that the area, again, it's got to be a closed loop, okay? The area inside that closed loop, even if it's this funky amoeba-looking thing, you can find the area inside of there, okay? As long as you can break this up into smooth paths, okay? And it's 1/2 times the line integral of x dy minus y dx. And that's just a formula you're going to write down on your note card, but I encourage you to look at the proof, see if you can understand it on page 1045, okay? Oh, man, just ripped my book. So, let's use this to, I'll switch to blue, find the area of the ellipse x squared over a, x squared over a, or is it a squared? Just, it's a squared, sorry. Plus y squared over b squared equals 1. So it's not an amoeba. It's some ellipse. Anyone remember the area of an ellipse? Okay. Well, it is pi AB. Okay. So now we do have to work to find the parametrization because we're going to use the line integral technique. So does anyone know or remember an ellipse in parametrics? Very similar to a circle. Excellent. It's a cosine t and b sine t. Okay? So, what would dx be? Negative a sine b. Sorry, sine t. And dy, positive b cosine t. Did I get my signs right? Okay, so now, look, this becomes kind of easy. Yes, dt on both of those. Thank you. Important. Okay? So look what we're about ready to do. We're going to find the area on that by calculating the work done over the line integral. Crazy. Okay? I mean, kind of. Half of it. Okay? So, what's our t doing? Yep. See, this is where you didn't have me for this. Chapter 9. Regular integrating in polars. Okay? So, it's the integral from 0 to 2 pi of x dy. So, what's x again, class? A cosine t times dy. B cosine t minus y. So, b sine t times negative a sine t. Are you seeing how? And then this is just dt times 1/2 out here. Thank you, Ratchet. Okay? And are you seeing how pretty this works out? It's the integral from 0 to 2 pi of a b times, can I just write a 1 there? Sine squared plus cosine squared dt. So it is a b t from 0 to 2 pi times 1/2, and that is a b times pi. Boom. Okay? Now, there is a little bit more to this that we're not going to go on the video, and it's going to get ugly. It's how to do this in 3 dimensions. So now imagine a loop that's also closed and positive so that when you're twisting around in space around this loop, the area is on your left. Okay? And we're going to just talk about that because it's not that important now, but it's going to be the foundation of the end of this chapter, which is Stokes' theorem. And I hope you're stoked for it. Can I get a boom? Boom. Boo. That was